谢谢汪一正老师的邀请以及热情的介绍。由于他有跟我讲说今天的 audience 是比较偏向专家类型的，所以说我今天讲的 talk 会稍微比较抽象一些，用了一些我觉得我蛮喜欢的一些数学工具。我今天要讲的是spin statistic theorem，但是对于 loop excitation。大家可以稍微看一下这个动画，这个动画对于我接下来的构造也会很有帮助。对。好，那我先做一个比较不这么正确的类比，就我们在讲连了。对，我有应该我有分享我屏幕，然后我的麦克风也开了。好。呃，一般来说，我们讨论这些统计性质，我们会用到所谓的 gravitational anomaly，叫做引力反常。就我先做一个比较不这么正确的类比。就当我们在高中的时候，我们先学过牛顿力学，讲的万有引力。我们的描述方式是说，当有两个物体有质量的时候，它们之间有个吸引力，反比于它们的距离平方。当我们学的比较深，比方说进入大学或研究所，我们学的爱因斯坦的广义相对论。对于这个现象有另外一个更深刻的描述，这其实是一个物体，它会使它附近的时空产生曲折，而这些曲折的时空会导致两个有质量的物体，它们之间会朝彼此运行。Oh, okay, sure, yeah. Okay, actually, English is maybe better for me because I don't know the terminology in Chinese. Okay, so I will try to describe this the Newtonian picture as some property. So it's like we try to observe the phenomena in nature, and we try to summarize some physics law. And for Einstein's general relativity, I would think it's more fundamental. So which means it gives us a deeper insight about how actually how actually the universe works. For example, the object in curved space-time. Okay, and now I want to consider a different problem. So as we first learned the quantum mechanics, when we try to solve the many particle wave function. So we know the particle has two types. One is called fermion, and one is called boson. So when we try to exchange the position of two particles, like here, uh, like here, so we can either get plus sign or minus sign. Yeah, so sometimes we just take it for given because we just say, okay, the phase factor of the wave function doesn't matter. So if we just try to exchange the position, it should go back to the original state up to some phase vector, and this factor is plus minus one. And today, I will try to give a even picture for this phenomena. So for example, what's the analog of this Einstein general relativity? So how do we use space-time to describe this process? Yeah. Okay, so the first part of my talk is about the statistics of particle, which is well known, but I just try to review and give a good starting point for all of us. So as I said before, when we learn the quantum mechanics, we say when we change the position of two fermions, we should get minus one. And due to the spin statistics theorem, the O fermion has the half integer spin. So which means when we rotate the particle by 2 pi, we should also get a minus one phase. So actually, this minus one and this minus one, they are not a coincidence. So they are linked to each other. So this theorem can be actually generalized for any, like in 2D, if a exchange of particle gives some phase factor theta, the spin must be theta. Yeah, so we can understand the spin statistics theorem by some following picture. So consider the ribbon here. So this is the ribbon twisted by 2 pi. And we can consider the other configuration, like this one. So when we try to stretch the ribbon in this direction, this configuration is actually equivalent to this one. Yeah, you can just do a little experiment. So you just prepare a very long paper and you first put it in this way, and then you try to stretch the paper. You can see, okay, this one is actually ready to this 2 pi rotation of the ribbon. Okay, so we can use this diagram to establish the spin statistics theorem. So first, let's consider the process here. So let's the vertical direction to be the time direction. And initially, we are from the vacuum, so there's no particle here. And as times go on, we create two particles. So we can treat this wall line, this ribbon as a wall line of a particle. And however, because the particle has some spin, so we can imagine there's some little error for each particle. So the wall line is actually the ribbon. It's kind of the thicker version of a line. Yeah. Okay. So let's try to interpret this process first. So from the vacuum, I create two particles, and then I rotate one of the particle, and then another again. So the left-hand side will get the phase factor of the spin due to the 2 pi twist here. And next, we can try to deform the ribbon diagram on the left-hand side into the right-hand side here. Yeah, so basically you can think of, we try to connect the ribbon from top to down, like this way. And this right-hand side is basically just this figure rotated by 2 pi or something. Sorry, pi over 2 or something. Yeah, so you can convince yourself these two configurations, they are actually the same. However, this figure will have a different interpretation. So consider, so again, we are in a vacuum. As the times go on, I create two pairs of particles. So we can think of I have a particle A inverse here, and the particle A and A inverse here. And now I try to exchange two particles of A like this way, and then annihilate with their partner again. So this diagram will describe exchange process. So we start from the vacuum, we create two pairs of particles, and which we exchange one of them, and then annihilate again. Yeah. So this ribbon diagram can actually help us to prove. So this is a very hand-wavy argument, but I think at least it shows some connection between the spin and exchange process. Yeah. So I think this is the simplest way we understand this phenomenon. And of course, so far I'm just talking about some space-time process, which seems very abstract and topological. But this process can actually be detected on the lattice. So let me describe the famous, this is called T-junction process proposed by Michael Levin and Xiaodong Wen back to 2003. So at that time, he tried to define some microscopic process which can detect the statistic of particles. So let's just consider this configuration. So it's a triangle with a center point. And initially, I have two particles positioned at vertex 1 and vertex 3. So here, this red particle and blue particle, they are actually identical. The reason why I use different color is just to help us to keep track of the position of particle. But actually, they are identical. So let me consider this process. So first, I move the red particle from 1 to 0 and from 0 to 2. And next, I move the blue particle from vertex 3 to 0 and 0 to 1. And finally, I move the position of this red particle from 2 to 0, like here, and 0 to 3. So if we compare the original and final configuration, their position exchange, like a red go from 1 to 3, and the blue go from 3 to 1. And more importantly, when I design this process, so you can see the operator I use like U1 here, and U1 inverse here, U2 inverse here, U2 here, U3 and U3 inverse here. So this process guarantees that any operator choice of this U1 or U2 or U3 doesn't matter. If I just modify U1 by some phase vector, like times its exponential I5, this will have the inverse phase vector here. Yeah, so this is a very robust process. No matter how you choose the position 1, 2, 3, or no matter how you choose the hopping operator U1, U2, U3. Yeah. Okay. And yeah, so there's a very important difference from here and the picture here, because on the lattice, we don't actually specify the framing. So we actually treat the particle as a particle. But implicitly, we can think of the particle as some a very tiny stick like here. So the particle has some orientation. And now if we follow the procedure I described in this figure A, and this little stick here will actually become the wall line, but it's a ribbon wall line. And actually, if you carefully follow the process here, you will see this wall line actually correspond to exactly the same ribbon I described to you. Yeah. Yeah.
So, it's possible that you become a matrix.
sorry. So here U is some hopping operator. You can think of it. It's like the Ci dagger Cj. So which hop the particle from 1 to 0. But this is just one example. On the torical, this U1 may be some Pauli operator, the tensor product Pauli operator. Yeah. So here is independent of model. It can be applied to any model as long as you have some hopping operator. Yeah, but yeah. So you can think of it as some matrix. Yeah. Okay. Now I will try to give some formal definition of fermion. Yeah. So let's consider first we assign some vector field in a space. And when I try to move the particle around this space, I need to specify the orientation of my particle consistent with this vector field. So for example, if I put a particle here, the arrow of my particle must be parallel to the vector field I define. And next, let me try to move this particle around this red circle. So you can see this blue arrow as my definition. Yes.
Are you restricting to certain specific Lattice models, or you're trying to define fermion more widely?
Yeah, at this point, I didn't specify any model. I just try to give some general picture to understand it.
It is in 2D?
So this works for arbitrary dimension, but for simplicity, we can just assume we are in 2D.
Okay, but then for your definition to both, there should be some kind of invariance in which your definition for this kind of exchange statistics should remain invariant. Otherwise,
yeah, that's a very good question. So I haven't put here, but actually this has some deformation invariant. So it's like a TQFT. When we try to do some retriangulation, we need to make sure the partition function is the same. And here we do have this process. So for example, you can consider embedding this triangle into some larger manifold, and you can try to deform your embedding, or you can try to move the position of this 1, 2, 3. We can actually prove that this is topological invariant. It's independent of how you embed, how you move this triangulation. Yeah, that's a very good question. And there's also a huge difference in 2D and 3D. Just in 2D, we can have anion. So which means this process can give you arbitrary U1 phase. And in 3D, we can only have fermion and boson, which means this process can be plus or minus 1. And if we work out this topological process like retriangulation carefully, we can actually prove this property. So in 2D, I think it's very naive, because in 3D, you can prepare this triangle and somehow deform it in a 3D space and flip this triangle. Yeah, and you can show that this is invariant. But if you look at the orientation, compare this one and this one, they are different by the inverse. So in 3D, which means this invariant mu need to equal to mu inverse. So which means mu can only be plus minus 1. Yeah, so you can use this topological property to give some constraint on the index you can compute from this process. Okay, thanks for the question. So let me try to continue. Okay, so let me try to describe a fermion in some formal way. So as I said that before, I require my fermion to obey my vector field I assigned initially. And when I try to move the fermion around a circle, this blue arrow is pointing always inward to the origin. So when we go around this circle, it has the 2-pi rotation of this particle. So we expect this fermion obtain some minus sign after you go around this circle. Okay, so how do we connect this to some formal mathematical object? And we can see the way he rotate is actually try to count the singularity of this vector field. So you can see initially I try to assign a vector field pointing inward to the 0 here. So this cannot be chosen globally there must be some singularity around the origin such that the vector field vanish. Yeah. So actually, the Steve-Whitney class actually count this singularity on the vector field. Yeah, so the name Steve-Whitney class may be kind of unfamiliar for physicists. So you can think of it's very similar to the chain class. The chain class for like quantum Hall effect, for example. The chain class is defined for every complex manifold. And similarly, for any real manifold, we can define some characteristic class called Steve-Whitney class. Yeah. So I think the formal way to define the fermion particle is actually can be written in this way. It's called dA equals W2. Yeah, so if you are not familiar with algebraic topology, this doesn't matter. This formula just means that when I try to move the particle along some trajectory in a space, I just need to count the number of singularity inside this a trajectory. And if it's even number, it doesn't acquire any minus sign. If it's odd number, this fermion will get a minus sign. Yeah. So this is just a formal way to.
This arrow.
Sorry. Oh.
What thing?
So here the black arrow is my input. I require when the particle move around space, the arrow of my particle must obey my black arrow. Yeah, of course, they have infinite way to assign this black arrow. So yeah, so another way to think is like first you move this particle along some path, and then along the path, this particle can kind of point in any direction, and after that you try to extend this direction into the 2D vector field. If there is some singularity inside, this particle must get a minus sign. If not,
the blue arrow is fermion on the center.
so here, this blue particle is the fermion, and because it's a fermion, it has some framing to kind of point, have some direction to show where is the fermion from point to. Yeah. Yeah, so this is some geometrical way to determine whether the fermion take on minus signs or not. I think the easiest one is we just focus on the particle, if it has some rotation, we give a minus one. Yeah, but if we also move it around the space, we can use this vector field description to tell whether it is a 2.1 or not.
What did delta A means?
Delta A means coboundary. So it's like the derivative. So when we learn the calculus, we learn some integral like dx and dy. This dx, dy is actually just like the delta here. Yeah. Yes.
Does this mean that we encode the data of spin of the particle into the background vector field?
Yeah, sort of, yes. Yeah. But this background field is not fixed. If you just try to move, for example, if I move my fermion like this way, it's always pointing up. And I can assign a vector field also point up. And then this will have no singularity, which means when fermion move around like this, it doesn't become minus one. Okay. And yeah, so this slide, I just want to emphasize this vector field can also work on the triangulation. So for any triangulation, we can assign some branching structure, and we can try to embed this branching structure into the 2D space. And we can also give us some singularity like here and there. Yeah, the details here is not important, but I just want to say my definition here actually work for the lattice triangulation. Okay, so this is a little bit technical. I want to review the higher Steve-Whitney class. So let me just give a geometric definition for Steve-Whitney class. So let me just make a statement. So the non-vanished case Steve-Whitney class means the abstraction to have some linear independent section of the tangent bundle on the n-dimensional manifold. Yeah. So you may heard of the W1. W1 is more often to to see in the physics. When I plus k equal to 1 here, so which means that W1 is an abstraction to have n-dimensional linear independent section on the tangent boundary of n-dimensional manifold. So which means when W1 is not equal to 0, there's no smooth assignment of n vector on n-dimensional manifold, which means it's not orientable. Yeah. So this is the object we encounter most often in physics. So sometimes we will write the action with W1, which means we consider non-orientable manifold or consider it as a time reversal symmetry. Yeah. And similarly, we can extend this definition for W2, W3, and so on.
If you're talking about math only, I think it's perhaps okay. You can define the quantity number on a discrete values.
Yes.
However, if you're talking about a vector field theory, then if your vector field theory may not have a continuous limit, I wonder if this would still apply. The usual definition of quantity number in vector field theory relies on that the field theory is continuous.
Right, that's a very good point. Yeah, actually, I prefer to work on lattice actually. Because in lattice, we can have this kind of operation I define here, and it's more easy for physicists to at least operate something. And yeah, although I draw this in some continuous limit, but everything like the W2 here or the vector field here can actually define on some discrete lattice. Yeah, so actually I try to make everything work on the lattice. It's more actually more clear and more well defined. Yeah. Yeah. So although the statement sounds like some continuous theory, but actually it can also define for the discrete lattice.
In your last slide, I want.
Your son?
If it is not a rentable manifold like Mobius string, if the particle winding around the whole string, there is a non-constructible
Yes.
loop, and the vector space, maybe it can it have two pair winding, but there is no singularity. I mean, space is around.
Yeah, so in that case, we need to consider how we embed this Mobius tree into 2D or 3D space. So actually, we can embed this Mobius tree into some 3D space, and we can try to extend this definition of vector field into some 3D space. So in that case, on the Mobius tree itself, it's hard to define whether this particle go around is plus sign or minus sign. It has some ambiguity due to some boundary condition. So we need to somehow embed it into some Euclidean space. But that's a very good point. In some manifold, we cannot define fermion. When we learn like a Dirac spinor in the QFT, we require the manifold to be spin manifold. So which means the W2 equals to 0, and then we can put a Dirac spinor onto this manifold. So in certain manifold without like a CP2, for example, this one has some non-vanished W2 class. So on the CP2, we cannot even put a fermion there. Yeah, so that's a very good point. So in certain manifold, we cannot have fermion.
That's a definition of
Yes.
the exercise. So is it like a requirement for WK is weaker when K gets larger? Does that mean if W1 equals 0, that means you can have n vector fields? It seems like obviously you would be able to have n minus 1 in a second.
Yes, I think so.
So W1 equals to 0.
Right, I think so. Yeah. That's a good question. I think of this question before, but I need to double check. Well, I think answer is yes. Or reverse. Yeah, because sometimes because here I work with I write W1. Sometimes it's homology, sometimes it's cohomology. I need to know the index, but I think one does imply the other.
I'm confused because I thought it was the other way around. When W1 vanishes, we talk about W2.
Right. So maybe it's due to some index here because yeah, I use some homology sometimes. Yeah. Okay. Now, so we just review the part one. So it's a statistic of particle, and I just try to give some mathematical definition for the fermion. And now let's talk about the statistics of a loop. So before I work on this, there are already many papers about this topic. So for example, in 2014, the paper by Wang Chenjie and Michael Levin, they discussed the three-loop braiding process. The three-loop braiding means, okay, maybe I discuss two loops first. The two loops mean when I have the loop alpha and beta, first I shrink the alpha a little bit and put it inside its beta and move the right-hand side. And next, I enlarge this alpha again and come back to the original position. So this is the so-called two-loop braiding. But unfortunately, in most of the case, this two-loop braiding is trivial because this process can slightly slowly deform to some trivial process, which means this alpha which can shrink to vacuum, so there's no alpha there, and then going through the beta and enlarge it again. And because here there's no alpha around, we can just move this beta circle to other place. So this two-loop braiding, in most cases, it becomes a trivial process like this one. The reason is because we can shrink this alpha to vacuum. So in this paper, they point out we need to consider the three-loop braiding like this, which means I have a little two-loop alpha and beta linking with the third loop gamma. And sorry, because of the presence of this gamma, the loop alpha cannot shrink to a vacuum. So which means this can give us some non-trivial process. Yeah. And also the other paper by Ye Peng and Xinsei Liu. Unfortunately, I don't know the first author. Yeah, so they also describe some different process in 3D. So it's called Brownian ring braiding. So basically, we consider two magnetic loop in the 3D space, and then I move the charged particle around these two loops to make some Brownian ring structure. And this can give us some non-trivial phase vector, characterize the 3+1D topological phase. Yeah. So both of these papers, they discuss the mutual process between loop. Like this is the process between three loop, and this is the process between two loop and one particle. And in my talk today, I want to study the statistics of the single loop. Yeah, I don't care about the mutual statistics. I want to study the self statistic. Okay, so this is my proposal. Yeah, so I think this proposal is kind of still recent. He only proposed around 2022, and I think there are still some debate. But let me just show our definition here. Okay, so the first definition. So let me describe the setup here. So remember, in the particle case, we have some hopping operator. When we apply the some operator U, this can move the particle from one position to the other one. And similarly, in the 2D, we have some membrane operator. Let's call it UN. When I apply the membrane operator UN on the membranes, which create a loop excitation around its boundary. Okay. Next, let me try to give two definitions or two properties of fermion loop. So first, I consider the loop. So the loop is positioned in this shape. And now I consider the pi rotation of this loop like this. So you can see this red arrow is kind of going to the reverse direction. And this blue arrow has also a reverse direction. So in other words, if I try to reverse the orientation of a certain loop, this will give a minus one. Yeah, so this definition is proposed by Fikowski, Hahn, and Hastings. Yeah, I will briefly describe the process later. Yeah. So naively, we can think of we create some loop here, and now I flip the loop, and this loop flipping will give it a minus sign, and we call this fermionic loop. And the other definition is defined by me and Xinbo Sen. So we use another way to describe fermion loop. So let me describe our definition here. So because I have some membrane operator which can define our loop operator on arbitrary manifold. So let's consider some unorientable manifold like a Mobius strip. And then we apply our membrane operator. So when the membrane here has some overlap with the orientation defect, like orientation reversing defect, the endpoint must hold some Fermionic particle. So this is our definition of the Fermion loop. Yeah. So these two properties sounds very different. Yeah, because one is about whether the loop flip can give a -1, and the other one is about when I apply this membrane operator on some defect, the endpoint of defect will have some Fermion excitation. And next, I will try to show the connection. Actually, try to argue these two properties. They are actually equivalent. Okay. So this is my setting here. First, I prepare a Mobius strip, and then I apply my membrane operator on this Mobius strip. According my property 2 here, on the orientation reversing defect of the Mobius strip, is the wall line of some fermion particle. And next, I prepare 2 copies of the Mobius strip. The blue one, like here, you can see the right-hand side and left-hand side, they are glued in different direction. And also, I prepare the other Mobius strip is in this green rectangle. So the right-hand side and left-hand side, they have some upward direction. And finally, I try to glue these two Mobius strips. So like in this edges of this blue rectangle, it's glued with this edge of green rectangle. And similarly, I also try to glue this direction when I compare into a small manifold. Okay, so once I glue this one, the wall line of fermion close like this figure 8. The we expect this process give us some -1 by our definition. Okay, so now I give you a few seconds to understand this process. First, I prepare 2 perpendicular Mobius strips, and then I try to glue their boundary. Yeah. So any guess which manifold of this one? Any conjecture? The hint is 2-dimension and it's not orientable. Any suggestion? Yeah. Among the 2-dimensional manifold, the only famous one which is non-orientable is either Klein-Bartel or RP2. And if you work carefully, you can actually see this is actually a Klein-Bartel. Yeah. Let me describe a way to see this one. So first, let me prepare 2 Mobius strips. So the red one here, the red one here is the rectangle, the left-hand and right-hand side, they are grouped in 3 ways. So this red one is 1 Mobius strip. And how about the blue one? For blue one, we first combine this red edge with this one. So we just move this triangle from bottom to top here. So this will become the edge of this. And the left side and right side, that's opposite direction. So the blue one also Mobius strip. So we can see we can decompose these 2 the Klein-Bartel into 2 Mobius strips like this way. Yeah. So this is a more usual viewpoint of Klein-Bartel. It's like it has some Bartel and going to inside and connect with like this. Yeah. So if we try to cut this Klein-Bartel vertically like this, so this is one half and this is the other half. And you can see this one half is actually a Mobius strip. Yeah. So it's a very fun way to visualize it. So if you just follow the orientation of this one, for example, follow along this way, you can see when we go across it, the inside point will become an outside point. Yeah, you can just do it by yourself. Okay, so let me try to establish the spin-set theorem for loop. So for Klein-Bartel, we have another physical interpretation. It's like just like previous time, we start from vacuum, and as time goes on, I try to create 2 loop operators. So in the right loop, it doesn't do anything, it just go to the end. And for the left loop, I need to apply some loop flipping procedure, and then inherit this. So in other words, this Klein-Bartle spacetime will actually describe the loop flipping picture of the definite. It's a property one. So remember, we define the fermionic loop by flipping property. Okay, so this is a cartoon picture for the spin statistics theorem for fermionic loop. On the one side, we describe this as some loop flipping procedure, and on the other side, we can try to describe this Klein-Bartle as some gluing of two perpendicular mobility. And this mobility, when we apply the membrane upright, it has some fermion on the orientation defect. Okay, so far, both two definitions sounds very abstract. But here, I just try to draw some space-time diagram. So you can just view this diagram exactly as the very early argument of this spin statistics theorem for particle. Yeah. So for the particle, this theorem comes from two different interpretation of the twisty ribbon. One is the spin, one is exchange. And for the loop case, we have two different interpretations of Klein-Bartle. One is the loop flipping, one is the perpendicular mobility. Okay, so how do I make this more practical? So similar to the T-junction process performed by Michael Levin and Xiaogang Wen, we also have another process which flip the orientation of the loop. Yeah, so you can see the conjunction is a little bit complicated. Okay, so before I find this sequence, there's another sequence in the Vygotsky Hastings original paper. They have the 36-step process which flip the orientation of the loop. And recently, I revisited this problem, and I think I used a different computational algorithm, and I find a shorter one. So this one requires only 22 steps to actually detect the loop conversion. So, okay, for example, let me start here. And then I apply some membrane. For example, when I apply 0.4, that means I will apply 50. And it will make this loop be formed into this shape. I forget the experiment setting. So here I put a 0 in the center of the diameter, and I can apply the membrane's upgrade phase. For example, on the 0.34, I will apply the membrane upgrade here, but the only loop from this to one, okay, like that. And we can put our context up to the end here. So on this conversion, I apply the loop, the membrane upright 0.14. So 0.14, I mean here. So I will erase this blue line and have another loop like in this one. So we can compare the arrow here. So remember, in this arrow, it's going this direction. The original arrow going opposite. So we can check carefully. Once I apply this sequence, the original loop direction and the final loop direction, they are reversed. And more importantly, I designed a sequence such that everything cancels out. For example, the N24 here apply once here, twice here, and also once here and twice here. So every process cancels out. Of course, you need to make it more careful because on each index, you want to make sure all dynamical part cancel. Yeah. So if you believe in me, this process is exactly the process described the Fermion loop on the lattice.
Okay, now you can.
Yeah.
So first we make some process we can shrink the loop doesn't want process is shrink. Why you cannot do it here? Like why you cannot just shrink the loop?
Yeah, because here this is the self-statistic of a loop. Because previous one, the problem here is if you try to detect a mutual statistic. For mutual one, if you can make one of them vanishing. So which is kind of grading is breaking bigger than bigger and here I only consider the single loop. Yeah, so the single loop. So the process I design here is always has a single loop configuration, but you can also consider some other process. So at certain point, the loop can also separate or vanish, but we can show that this is still some topological invariant. Due to the you can ask the same question about the T-junction process. In this case, I can apply the operator between 1 and 3 to make it two particle dynamics. Yeah, so this is still can go to breaking, but this can still give you some non-trivial units. Okay, and now in the maybe less 10 to 20 minutes, I just try to give you some example to demonstrate this Fermion loop is actually not that unusual. So actually, the Fermion loop even appear in a 3+1D Z tutorial. Okay, so yeah, so let me first describe the Hamiltonian. So consider a 3D cubic lattice, and we pull a Pauli matrix on its edges. So first, we have the Pauli X star turn, so which means it's part of X around the vertex. When we have the Z part K turn like this, so it's a part of Z around the face. So in this model, we have two types of excitation. One is the electric charge excitation, and the other one is magnetic flux excitation. And notice in a 3+1D, the charge is a particle, the flux is a loop. So this is they operate on the lattice. We can apply this Pauli X to excite this membrane operate. Sorry, so this K turn around the boundary. And here, when we apply some Z3, the endpoint will violate start. So this is the operate for particle and loop. So in this case, this is bosonic, and I will try to make them become fermionic later. Okay, so this is my proposal for definition for fermionic excitation. For particle, we use the second Stephen-Winning class to define the fermion to get the minus sign on that. And similarly, we can use, it's very naive to generalize into the higher dimension. We can use the third Stephen-Winning class to determine whether a loop can pick up a minus sign. Yeah, but I will skip the mathematical detail here. I just try to show my proposal. And actually, this proposal is not invented by me. It's first mentioned in the Ryan Songen's paper back to 2014. Okay. Okay, so maybe for the last few slides, I just deal with some technical calculation. And so here I try to use some topological action to describe how do we make a theory become fermionic. Yeah. Okay, so the formula is a little bit technical, but I will try to explain. So first, the first term is the standard torical Hamiltonian. If there's no second term here, the first term I described before actually give you two equations of motion, the dA equals to 0 and dB equals to 0 here and there. So in this model, everything is bosonic. And now I can try to twist this term by some topological action. So this is very similar to the 3T quantum double. So given a torical, we try to insert some cocycle to make it twisted. And this cocycle can actually modify the statistic of particle and loop also. Yeah. For example, in this case, if I try to add one more term, this will change the equation of motion with delta A equal to W2 and delta B equal to 0. So which means the fermion is a fermion, the particle is fermion here. How do I tell, like from this equation of motion is a fermion? So first, we can try to detect this anomaly by gauging. By gauging means I couple to some background gauge field A, such that the gauge, it has some gauge information, which is B and A3. Yeah. So when I try to add this gauge field, the first term here is some anomaly. So which means it's not get invariant. And we need to use a higher dimensional term to cancel out the anomaly here. So this is the pretty standard technique in hydrogen physics. It's called anomaly inflow. The surface anomaly is equal to the bulk anomaly. Yeah. And yeah, so let me just ignore some technical detail. And the final answer is this action in the bulk can be somehow reduced to something like this. And this has a very clear geometrical meaning. So yeah, let me just do some movie. So consider I have some wall line of the particle A2 and A2 prime. So A2 is the wall line, A2 prime is framing. By framing it means I just shift this line a little bit to form a ribbon, please. So here, there's no twist. And the final is some 2 pi twist. If we go from here to here, I need to slowly deform this purple framing. However, due to the 2 pi framing here, at certain point, these two lines must touch. So when this touch, this is captured by this turn A2 cup A2. So yeah, so in other words, when we try to gauge the theory, it has some anomaly in one higher dimension, and the one higher dimension can be interpreted like this. So whenever I have the two go from the no twist with twist, we get a minus sign. Yeah, so this is the geometrical interpretation of my formula here. Yeah, but the calculation is very technical. I don't want to go to detail, but I just want to show I have some nice process which can describe the behavior of fermion on the field theory. And similarly, I can make this model into some lattice Hamiltonian, just like torical. So if you just try to ignore the poly X here, it's just exactly the same as a 3D torical. And now I just try to trace this pattern by some additional poly extent. This will make this particle become fermionic. Yeah, so this is called fermionic torical. So in this 3+1D lattice model, the charge is a fermion, but loop is still bosonic. And similarly, for the loop, we can do the same thing, but it's a little much more complicated calculation. And I don't want to explain here, the time is not allowed. And I just want to show I have a similar figure. It's related to the Klein-Bartel. So it's like on the orientation defect of Klein-Bartel, I can also define this kind of twisty winding number. And this twisty winding number is actually related to the process I described to you. And finally, I showed that in certain model, like a torical. So you can actually verify. So this is one special excitation in a torical. Actually, it's equivalent with the end loop, but it's different by and you can plug in this excitation to my process defined here. This actually give you -1. Yeah, so even in a very simple 3+1D torical, it does give you some fermionic loop excitation. Okay, so this is my last slide. I just want to review what I have talked today. So first, I review the well-known spin statistics theorem of particle. It's just two different interpretations of the twisty ribbon. And now I generalize this argument into one high dimension. So we use the Klein-Bartel. From two different interpretations of Klein-Bartel, we can describe the fermionic loop with these two properties. The one is the loop flipping, give you -1. The other one is on the mobility, you have some fermionic excitation. Yeah. And I try to use some formal mathematical object called Stephen-Winning case, actually the second and third Stephen-Winning case, to define the fermion particle and fermionic loop. Yeah, and okay, in the last 2 points, I didn't actually go through. Yeah, so I can describe many beyond chromatic excitation, like W2, W3, using this kind of technique. And also in the future, actually, it's what I am working on is I try to generalize into some higher dimension. For example, I am working with Qinrui Wang and Chen Meng. We want to show that in the 4+1 dimension, if we consider the membrane excitation, the membrane excitation has some Z2 invariant related to W4. And more interesting is another Z3 index related to the Pontryagin class. So actually the membrane excitation is even richer. So we know the particle has a Z2 fermion boson. For membrane, it's actually Z2 times Z3. Yeah, it has more topology invariant we can play around with. Yeah, but we haven't finished yet. Okay, thank you for your attention.
Thanks, Professor and for this
Yes.
Can you explain the line where you define I mean, you say the defect line.
Different.
Intersect with the
Oh.
boundary of the bulb strip. And you say that there is
Let me see. Here?
I don't know, so the red line is the defect. For example, you have a polyet and the more strip is a membrane of critical.
Yeah.
And so the red, so what is the red line? It's a defect that you put in your model.
Yeah, that's a very good question. So here, my 3D spacetime, my 3D spatial manifold is orientable, but we can consider the Mobius strip embedded in this 3D space. It's totally fine. You can just imagine there's a Mobius strip here. And now, when I define my membrane array here on every face, I actually require some orientation. For example, if I assign some orientation here, and I apply my membrane here, and then the other face has orientation here, I apply my membrane here to connect them. However, if I try to apply this on the Mobius strip, when we go around this one, the left-hand side and right-hand side, the orientation of the membrane array, they are actually reversed. So there's a defect here.
Oh.
So this is the defect of the array you apply. It's not a defect of the spatial manifold.
So okay, like this, that is what do you realize?
Yes, we can write it like yes.
Another question.
Yes.
I don't know why would copy operation.
I can do what?
Copy operation.
Copy.
You mean the data is high. You mean you have Mobius, then you copy.
Oh, I think I prepared another one. So you can think of here, I just apply my membrane array on certain surface. So I can prepare the other one. So the other surface may be there. They have some intersection. So these two membrane array, they do have some intersection. It is fine.
Then why you can group the two sides?
Oh, by gluing means I just try to design my Mobius strip to okay. So I can deform this surface. So I deform these two rectangular such that their edge they coincide.
Oh.
So this is just some open membranes on some 3D spatial manifold, and I have some freedom to make it like flexible, and I can deform this shape to make that this shape from like the green.
In 3+1D, can you actually link your definition of fermion boson to the usual spin statistics?
By usual, what do you mean by Lorentz symmetry or something?
Yeah, because that's due to causality.
Yeah, that's a good question. Yeah, that's a confusion because someone told me the Lorentz symmetry is important. Only with the Lorentz symmetry, you can have the linking with the spin and statistics. Otherwise, on condensed matter physics, we can talk about spinless fermion, and no one can.
Spin statistics theorem, causality is more important than just Lorentz covariance.
Yeah, actually, I don't know because for that one, it's purely continuous field theory. Like, but here, by fermion, I actually mean this one. Yeah.
Because Lorentz covariance itself cannot imply causality.
Yeah, I don't know here because but actually one important thing is the locality. Yeah, so we can forget about any physics I learned. I just try to study with this lattice model and want to show that this is some topology invariant. So we can do the following thing. So first, on the lattice, we just try to define my operator, which can be full of any link. And later, I can study the relation between this operator. For example, the operator of this 2, 3 need to commute with the operator of 0, 1. So this has some locality. So once I impose this O constraint, like a 2, 3 commute with 0, 0, 1, 1, 3 commute with 0, 0, 2.
So
What's-
locality is more.
Yes, yes.
Access. Causality is more like a global feature of the space.
Yeah, but actually the causality imply locality in some sense. The reason is following. So let's consider I have some finite depth unitary system, just U01 and U23. And when they intersect, their commutator will only depend on the region around their intersection. This is due to the Lie-Robertson bound.
Yeah. I think perhaps you can go from that direction. When we're talking about.
Yeah, exactly.
To
Yeah.
define the lattice.
Yeah.
To link to.
Yeah, that's a good point. Yeah. Yes.
Any more questions?
So I want to know how the vector field can be distributed in the 3D version.
Yeah, that's a good point. So I don't have a figure here, but it's related to the definition of stable cat. So similarly, you can define certain S, which is basically how you assign your vector field. So in 3D, it's not only the vector field. You need to assign 2 independent vector on each point to define a W2, for example. Yeah, and you can then say around the edges, it has some winding or not. If it has some winding, which means it has some singularity. Yeah, so yeah, this is totally doable in high dimension. Yeah. Maybe I can show you some figure. So it's do I have internet here? Yes. 1 second. That's inside my other paper. Sorry, this one. Okay, sorry, the internet is slow. Okay, fine. Sorry, let me try to find a figure I refer. Sorry, I cannot find it now. Maybe I will show you later.
Another question is, can this procedure be reproduced in other screen modes like?
Sorry, other one.
Can this procedure of promoting sonic loop to reality and examining this self-static properties can this be reproduced in other 3D models like SQ?
Yes. Oh, sorry. You mean a fractal model?
Yeah.
Yeah, that's a good question. I just discussed with Song Hao. Yeah, I think Song Hao, he has a paper about defining the fractal. Yeah. So this is related to the procedure I told to Professor Yidun. So we use a locality. So first we just define O operator, and then I define O relation between them due to locality. So once you have all this set up, you can let the computer to find the invariant. Actually, it's a very straightforward computation. You just list all your invariant and list all relation, and you just compute some Smith normal form, and this can output the process. For example, the 24-step process and the T-junction process can all be computed by the same methods. But for fractal, I haven't tried because I think it requires a larger dimension. So I believe it should work there.
new spaces. If no questions anymore, let's take the proposition again.
Yeah, thank you. Yeah. By the way, I found a figure. So here's a question: how do we assign a vector field in 3D? Yeah. So similar thing can be done in the 3D triangulation, and we can define when we go around a certain line whether it has some winding or not. Yeah.